You ready?
Hello, and welcome back. July, and we are back this time with very exciting talk on containers runtime security. As usual, I would like to start the session by giving a shout out to all of our sponsors, PwC, Google, Atlassian, Amazon, and SecTeam, and to you guys who have joined us for the past few months since we went online. One thing to mention, we are looking for speakers for the next few months until effectively end of this year. So that will be August, September, October, and most likely November. So if you can do a talk or something that you present on, it could be a short talk, lightning talk, please do reach out. You can either email us at Sydney@SecTalks.org, or you can just head to our CFP page, which is j.mp/SecTalksCFP. There are those links at the moment. You can see it on your screen. Like before, we will be using IRC as a main place to ask questions. So if you have any comments, if you have any question for the speaker, please hop on the IRC, and you will see the link for the IRC momentarily on the screen. You can also go to sectalks.org, scroll down toward the bottom of the page, and you will see a link for a web client IRC in case you don't have an IRC channel, IRC client. Alternatively, you can also ask your questions on SecTalks Sydney Slack channel. And if you don't have access to any of those, still you can post your question on YouTube, and one of the organizers will take the questions from there and will ask from our speaker. Now with that, I don't want to take more time. Let me just go straight to the talk for this evening. The speaker we have tonight, I've been chasing him down for over a year now to bringing him back. He has presented in early days when we started SecTalks Sydney. I guess that goes back to 2015. And at the time, we were quite amazed by some of the CVEs that he published and he talked about, specifically to do with all the parse resolution to do with the container escapes that he came up with. And now he's back, this time with more content and exciting enough on the defensive side as well, to just tell us a little bit about how he, at the moment, managed to address the current issues with the parse resolution or this class of vulnerabilities in containers world. So he will be talking about container runtime security, and he will be speaking about effectively one of the main things that the containers, apart from many other things they share, that virtual file server file system layer. And we will talking about that, a class of vulnerabilities that is specifically related to that. And I'm quite excited to hear about some of his own mitigations and defensive measures that he thought about and he engineered and put it in place. He's a core developer and maintainer of RunC, and he's a maintainer of the Open Container Initiative, or OCI. And he has been working with Suzy for a while now and working on the core parts of the container, lower level part of the container. Apart from that, he's being committed to the open and a strong proponent of the free software. So with that, what I would like to do to welcome Alexei Sarai, or I guess Cypher for some of us which we know him, on the stage to talk about the container runtime security.
Hi everyone. Yeah, it's great to be back at SecTalks, and yeah, it's been a while, Pedram. As it's funny you mentioned the first talk I gave, because I think when you watch this, you'll be this will look very familiar to you. It'll bring back some nostalgia, let's put it like that. But yeah, so let's kick it off. Right. So yeah, so as Pedram mentioned, this is about security and container runtimes. This will be a fairly whirlwind tour of a huge variety of issues that we've had with container runtimes over the years, as well as some of the things that are keeping me up at night, in particular path resolution. So let's kick it off. Now, this is going to be mostly focused on how we've mitigated some of these issues, because there are a lot of ways that you can attack container runtimes, but I think it's interesting to speak about the ways we try to defend against these things. So before we start, if there are any ops people in the room, which there may or may not be, I would suggest if there's one thing that you should take away from this talk, you can go to sleep immediately afterwards, is please use user namespaces for the love of God. User namespaces are a security primitive on Linux, which are possibly the simplest mitigation you can have for. Sorry, oh, yeah, okay. I'm sorry, I was double checking that Chrome's been crashing recently. Yeah, so user namespaces are possibly the most simple and straightforward security mechanism you can enable for containers under Linux. User namespaces are effectively a method by which containers run with a different set of UIDs and GIDs, which, in addition to meaning that if you break out of the container, a process running inside a container that is running as root is actually running as a different UID and GID on the host, meaning they can't do all sorts of regular attacks. But in addition, it also allows you to isolate between containers, as well as many of the kernel issues that I'm going to mention in this talk. The mitigations in kernel require users to be using user namespaces. If you go and you read, mailing list threads on LKML about about these sorts of security issues that, when we discover a security issue related to the kernel, we discuss it with the upstream community in Linux. And you read these mailing list threads, and basically there is an assumption by kernel developers who are developing these security features that user namespaces are on, that everyone uses them, and that you would be stupid not to use them. So please use them. That's the end of the PSA for today. So, and yeah, right. One of the things is that quite a few of the bugs that I'm going to mention today actually were protected against by user namespaces. So even though we may have made mistakes in container runtimes, user namespaces still would have protected you. So I think anyone who's ever seen a talk about containers ever in their life has seen the first 5 slides of a talk, which basically goes through what namespaces and C groups are. For those who don't know what those are, I'm not going to go into them now because I think most people are getting bored with this discussion. But in short, they're both security primitives on Linux, which make up a container. Containers aren't necessarily aren't really a concept. Oops, Chrome crashed. Sorry about that. Chrome crashed. Hopefully it doesn't become a repeat problem. Yep, sorry, what was I saying? Yeah, so container runtimes. Yeah, so effectively, yes, so they're security primitives on Linux, and in general, a container is nothing more than a process which is running inside these things. The key thing I want to take away here, and I'm going to give you like a PDF version of a container runtime right here, is that container runtimes are that they have to do a lot of complicated operations with a container in order to set it up and in order to make it make the final container you end up running. So the first thing that a container runtime has to do is it has to download and extract the image into some rootfs. So there is basically the image you download gets extracted into a directory. This is usually done using Btrfs or ZFS or AUFS or OverlayFS. Basically, there are in-kernel file systems to make this more efficient, but in general, it's basically a tar archive that gets extracted into a directory, and that's the root of your container. And then everything that follows on from there is basically the process of creating a container. These processes are sort of like a more sophisticated chroot, effectively. So if you have an idea of what a chroot does and how it interacts with the system, this is basically a more complicated and more secure version of it. That's all a container is. So the container runtime, you have this process which has now extracted the rootfs, and then this process, which is in our case is runC, which is the runtime underneath Docker, but this is true of basically any runtime, is that they create, is that you have this process which then forks and creates a proto-PID1. This is the process which will end up, after all the setup steps, will end up being the process that actually runs your code. So, and there is this parent process in the host, which is assisting with this setup procedure. So you have a process which has spawned something, and then that thing that spawned continues doing some setup, and the parent helps with some setup because there's some privileged reasons why a container can't do it all on its own. So once you've done that, the parent's job is effectively to move the process into the correct C group. So C groups, as I mentioned, are a primitive in Linux to do with, they basically have to do with like memory limits and stuff. It's something which is important, but the details of which are not really that interesting. It's basically just a way of saying these processes have these limits, but the parent does this setup. It then sets up networking because networking is quite a complicated thing to have to set up. So it'll set up either like regular bridge networking, which is how Docker works, or it'll set up something else. And then once all this setup is done, there are quite a few things I haven't mentioned here, but after all this setup is done, it gives a signal to the child saying, okay, you can get started now. And then the child will exec VE the user's code. And then on the child side of things, the child has to create or join whatever namespaces have to be, it needs to join. So it has to create the mount namespace, PID namespace, networking namespace, IPC, and hopefully, if you listened to me at the beginning, you'll be using user namespaces. And it creates these or joins them. In the case of when you do like Docker exec or kubectl exec, when you're joining an existing container, what that operation is doing is that it's basically creating a process rather than that process creating a new namespace. It's just joining an existing one. And then once these namespaces are set up, then it has to construct like effectively all of the things that you expect in a container. It has to set up all the mount points for the container process. It has to set up, procfs, sysfs. It has to set up everything else. And then it pivot routes into the new rootfs. This rootfs is the rootfs you extracted. And that rootfs pivot routes is a new system on Linux. It's like probably 10 years old, but newer than chroot. It's basically like chroot, but it's more secure for a variety of reasons. And then after that, then we get into all of the like even more crap that we have to do in terms of container runtimes. You have to configure seccomp, which is a security mechanism that that actually by default is on in Docker, but whatever, seccomp, LSM, so that's AppArmor or SC Linux or Yamato or whatever, Tomoyo or whatever you want to use. No new privs, which is another security bit on Linux, and then processor credentials, so changing to the right user and all the rest of it. And then, as I said, child waits for the parent, and then executes the user code. And yeah, there are a couple of other jobs. So as I mentioned, container runtimes sometimes have to spawn a new process inside a container while it's running. And this is very key, is to note that there is potentially untrusted code running inside the container at the point when you're trying to join it, which means that from a trust perspective, you have to be very, very careful that this container is not, this container doesn't do anything dangerous while the container runtime is joining. And yeah, once you're doing these joining things, another thing is that container runtimes have to do is they have to do updates to containers. So this is a feature which I think is not as used as widely as maybe you would expect. But there is like this Docker update feature or kubectl that's through the whole complicated system they have for updating things. Basically, if you want to change the limits on a container, you have to start modifying the state of the container while it's running again. And there's a whole bunch of really boring stuff that we do inside container runtimes. So the key takeaway here should be that there is a lot of annoying little bits and steps that we have to do inside container runtimes. And getting any of these wrong can be quite bad because each one that you miss, if you forget to do one, or if you do them in the wrong order in some cases, you end up with a security vulnerability. In addition, the other problem is that this fact that the container is running and all of these operations I've mentioned, which may sound like a lot, all of these operations are all inatomic, meaning that you have to do them one by one. And while you're doing them, the container code is still running. It can do all sorts of dangerous things to you, or well, not necessarily do them to you, but it can try to trick you is the way I would put it. So we're going to now go through a whirlwind tour of CVEs, trying to sort of get an idea of what types of things are common to all of them. So this is actually the CV that Pedro mentioned that I gave a talk about quite a while ago. And yeah, I think it was in 2015. Sorry about that. Yeah. Yeah, okay. Sorry about that. Yeah, so anyway, Pedro mentioned this this security bug earlier. Effectively, it was possibly the dumbest one you can imagine, which is that Dhaka CP, which is a thing that lets you copy files into and out of the container. It just basically didn't do any path sanitization whatsoever at all. Like you could do, the SYD 101 thing of just slash dot dot slash dot dot slash, and you would get to the host file system, and then you could read anything from the host that you like. There was a similar bug, which was that you could write to anything using Docker files. You could trick the builder into copying to any file on the host, so you could even overwrite files. Basic lesson is maybe we should, sanitize path a little bit. Seems like a good idea. But okay, we get that's sort of an obvious bug, and it's bad, but whatever. We fixed it, all good. Then there's like in 2015, there was a whole slew of awful CVEs, all of which were basically related to, we had misconfigured containers. So the point here that I'm trying to make, and I'm not going into the details here because they're actually all very boring in terms of what the actual security bug was. I mean, it was like silly shit. Like we'd forgotten to, in some cases, we'd forgotten to set a security flag, which we had like added support for, but we just set it to 0 rather than 1, like stupid stuff like that. These configuration issues are just sort of examples that we have to be very careful when writing container runtimes, which is hopefully sort of obvious. It's a fairly important piece of software in today's age. But yeah, you need to be careful of this. And yeah, containers are hard. And one of the issues was with the volume instruction in Docker files, which lets you set up volumes between containers. That was I think 2 or 3 of them actually had issues with specifically that. And you can tell, obviously, that given the nearly sequential set of CVs, these were all discovered in like 1 week. So it was pretty bad. And actually, they were all created and discovered in the same release. Like it was just one release that had all these CVs. It was pretty funny. Okay, now we get to some of the more complicated CVs. So this is one that I discovered in 2016, which was effectively the issue was that we had a container runtime. So as I mentioned, a container runtime, when it's joining the container, you have this proto-PID1 process, which is spawned by the container and is slowly setting itself up to join a container. As it's joining a container, we had accidentally kept open a file descriptor to the root file system. So this was basically, we had opened a directory on the host, and then this process is joining the container. And it turns out that there is, in /proc, which is procfs, you can actually access the file descriptors of another process. And long story short, while this process was joining the container code inside the container could just go straight through the procfs, and go to the host file system. And once you go through this file descriptor that's on the host file system, as Pedro mentioned, one of the things that is common on Linux between containers, again, containers are not like VMs in that there isn't a separate kernel running. Containers are basically a program that is running on the same kernel as everything else that has some little bits of trickery to try to make it so that that it thinks it's the entire system. And every single time it tries to open a file or do things, it gets lied to by the operating system. But these file handles that you get from outside the container, they're still real file handles, and so you can go through them to access the host file system. And this is pretty bad. We managed to fix it. using a feature called a non-dumpable bit, which is basically, it has to do with debugging, funnily enough. But basically, you can block this access by setting yourself as non-dumpable. Though actually, funnily enough, there was actually some kernel bugs here as well. It turns out that the non-dumpable bit is cleared when you exec a new program. So when you do exec another program, this happened this clearing happened before you closed all the file descriptors that were marked to be closed for clo-exec. So when you open a file, you can mark it as close this when I exec a new program. And there was a race condition where, because the kernel would do these in the wrong order, you would have a window where the non-dumpable bit is cleared and the file is still open, so the container could still access the host. And it was something like there was like a 3% chance that you could access the host anyway. So we had to fix that as well. But the long story, or the short story, is that procfs is pretty scary, I would say. It's kind of freaky how many things are possible through procfs. And this will become a running theme, I think you'll find, throughout the rest of this sort of whirlwind tour. So, okay. In 2017, there were quite a few Kubernetes CVs, I think 3 or 4. That were all related to symlinks. It was basically the same Dhaka CP bug, but with Kubernetes. There's not really much to go in here. It was just sort of, lol, they forgot to do these checks. They added some protections for it, and I didn't look this up before the talk, but I think that there were bugs in this in a year or two later that were discovered, which was a continuation of the same issue, but whatever. They've sort of fixed it. Kind of sucks that they didn't sort of go deeper and try to solve the deeper problem, but they just sort of blocked it and said it's fine. Okay, then we come to 2018, and this is sort of the return of the original attack I discovered in 2014 that I spoke about at SecTalks last time. Basically, it turns out that just sanitizing the path isn't enough if the attacker can swap the paths underneath you. So if you have a file system which the attacker can create files and move files, move being the most important thing here, if you can move files in the container while the container runtime is trying to do something on the file system, that can be very bad, because this path sanitization that you do, where you sort of walk down the path and be like, oh, is this a symlink? Oh, okay, I'll swap the symlink out with something else. I'll clean up this path. The problem is that after you've cleaned up this path, the path might have changed afterwards, and there's nothing you can do about it because it's a fundamental race condition. I mean, it's a time of check, time of use attack. Almost like a textbook example of one. So path sanitization isn't enough, and turns out that in particular rename exchange, which is a newish feature on Linux, that you could have done this without rename exchange, but basically you can swap a directory component with a symlink and thus trick this path sanitization. So to get a better idea of what this looks like, I hope you will excuse my awful graphics. Basically, if we imagine that we have some like foo directory, which is the directory that is safe. It's a foo directory that is like on the host, and that's the container rootfs. And then inside you have bar and baz, and so these are like regular directories. And then you also have /bar2, which is a symlink that the attacker has created to /etc. And this is all done inside the container. And the attacker, here shown as the Kali Linux logo, they are doing rename exchange between /bar and /bar2. So they're constantly swapping bar and bar2 back and forth at the same time as the container runtime is trying to open foo bar password, okay? Or I guess foo bar shadow is the better example, but whatever. What happens is that the container runtime says at some point is opening foo bar, and they're like, oh, is bar a symlink? And if you hit the race window just right, it'll go, oh, bar isn't a symlink because it's a directory. And then it cleans up the path, and the final sanitized path is foo bar password. But then the symlink, the file gets swapped with a symlink. And then when it goes to open it, because it's now sanitized it, and then it goes to open it, when it goes to open it, it finds out that, oh, I've accidentally opened etc password on the host. Because remember, the container runtime is executing on the host. So if it hits a symlink, that symlink is resolved on the host file system. And this bug was present in Docker. You could trigger it fairly easily. And this is this is a CV that I discovered. I don't know if I mentioned that already. This is a CV I discovered in 2018, and it was very similar to the old Dhaka CP CV that I'd helped fix several years prior. Okay, So what was sort of the lesson learned from this one? Basically, part-time isn't enough, especially when you have an attacker in the file system. And we need to figure out a better way of doing it. But it turns out that solving this properly is actually quite non-trivial. So LXD is an alternative container runtime that is the Canonical folks work on. And they do a lot of really brilliant engineering, in my opinion. But in particular, they do actually have protections against this sort of thing. But if you go and you read the code, it's very complicated to get right. Like, it's very, very difficult to get right. And the way that they've done it is that they've open coded it. So you basically every single time they have to access a container, a file inside a container, they have these like giant functions that are just trying to make this thing safe. Now, those implementations, as far as I can tell, are safe. But the fact that these aren't like open coded and all the rest of it is a bit of a worry. And also in Docker, we didn't solve this problem by actually fixing it properly. The solution was to sort of clean up some of the CH. It turns out this bug was actually not just like, it's a fundamental flaw in how Docker thinks about files inside the container, because it thinks that sanitizing them is like an operation that makes sense. But in addition, there was also a second bug in chroot_archive, which is basically the library that they use to extract files into and out of the container. So they fixed chroot_archive. So Docker CP is now protected against, but the underlying assumption or the underlying bug still remains. There is still an issue in Docker, which is that they still think or the code still thinks in terms of, oh, I'm going to take this path that's in the container and I'm going to sanitize it to a host valid path, and then I'm going to operate on it later, which has this fundamental race condition I mentioned. Okay, and now we get to last year. Before everything caught on fire. So last year, and this is now again, as you might notice, a lot of these attacks are refinements of early attacks. So this is a refinement of the last proc self attack I mentioned. So basically, the issue was that okay, there is this non-dumpable bit. So in theory, we can't open any of the files in proc. So when the container is joining when the process is joining the container, it can't, any process inside the container can't touch any of the procfs files for that process. That's what non-dumpable does. So, okay, some researchers figured out a very clever trick to get around this, which was that, okay, the non-dumpable bit is cleared on exec_ve. So what they could do is they could just get the container runtime to exec itself. So what you do is that rather than doing like Docker run, of some program like bash, you instead do Docker run of proc self_exe. And what happens is that proc self_exe gets re-executed. It clears the non-dumpable bit, but proc self_exe still points to the binary on the host file system, because that's what proc self_exe is. It's what's called a magic link. It's a symlink that actually takes you through to the underlying file. And I'll go through magic links a bit more in a little bit. But basically, this proc self_exe is actually pointing to the host file system. And because the non-dumpable bit is cleared, you can now open this thing read-only or with opath. Now, you can't open it for writing because on Linux, you can't open files that are currently an executable, that are currently the memory of an executable. You can't open them for writing. So instead, what you do is that you open it for read-only, and then you get the program to execute something else. So it'll exec some other program. And then afterwards, you open it for writing. And the way you do this is that there is this mechanism in Linux, which is file descriptor reopening. It's actually, I'm pretty sure it's a bug. It seems like a bug each time you use it, but basically it allows you to, if you have an open file, you can go to proc self_fd blah, and then open that. And that will allow you to reopen it. If it was read-only, you can reopen it as write-only or read-write. And as a result, this attack allowed a container runtime to overwrite the host binary of runc, which means that next time that Docker does any container operation, you're running code as root on the host. It was a very clever attack, quite ingenious. And unfortunately, the solutions for this are quite iffy. And Google in particular was very unhappy with how we solved this the first time. Key thing is that procfs, again, is terrifying. I mean, it's pretty scary what sort of things you can do with it. And then the way that we fix this problem is that we would make a copy of the binary so that when you overwrite it, so we figured out there's not really a way to stop the binary from being overwritten. At least there's no way that isn't like foolproof. So instead, we make a copy of the binary, and then so if you overwrite, it doesn't affect the host file system. Google didn't like this, and quite a few other cloud vendors didn't like this because it like increased the memory usage of containers by like 10 megs because runc is a Go binary, and Go binaries are massive, so you end up with 10 megs or 5 megs bigger thing. It was pretty bad because creating a temporary file uses up the memory accounting for the container. Anyway, so we figured out ways of hacking around this with read-only bind mounts, but ultimately the protections are less than ideal. Ideally, it would just be that the kernel wouldn't allow you to do this bloody thing. Like, why is it possible for me to open an executable, which I, by definition, cannot write to, and then later open up for writing? It seems like this is something that shouldn't be allowed. And actually, I've posted some kernel patches to block this. The discussion is still ongoing. But it's, in theory, it's something which I think people aren't against blocking it, but I think that there needs to be a longer form discussion about how to actually protect these things. Okay, and then 2019 again. So this was another clever trick which was discovered by some of the researchers, which was that we have to, so in procfs, aside from being a source of pain and agony, procfs is also important when it comes to setting up containers, because one of the things we have to set up is LSM labels, which are security labels for a process. And the way you set them is you write to proc self @exec, which is a file, or proc pid @exec. So you write to the process's procfs saying, this is the attribute you should have when you exec yourself. But it turns out what you could do is you could just put a volume statement in a Docker file, and then the volume could then go over procfs files. And what this would allow you to do is that when the container is started, the volume directive ends up configuring the mounts such that procfs gets mounted over, and this happens before the security labels are set. And this is we can't do it before because mounting isn't allowed with security labels set, so we have to do it afterwards. But as a result, you can get things to be mounted over, and then you try to write to it, and then it writes to like an empty file, and then you've now been tricked into running a container that doesn't have security labels set, which can be bad, especially if you have a kernel 0-day or if you have other attacks available to you. So that was pretty bad. And yeah, procfs, while it might be horrifying, it also can be faked, it turns out. And this is also quite a clever trick. The way we solved this one is that a bunch of checks that are sort of dodgy, which are basically, we don't allow things to be mounted over proc. So you can't mount things on top of procfs unless they're also parts of procfs or they're a bind mount. Basically, because of the ways the containers are set up, we have to come up with these sorts of dirty hacks to make it so that we can still allow most containers to run without breaking the security of them. And in addition, we added some checks to make sure that the target, if you try to write to these procfs files, the target of writing to them must be a actual procfs file. So in other words, if you try to write to a file and it's actually a tempfs file, or it's not on the procfs file system, then it'll give you an error. Unfortunately, the next CV we had was basically just an extension of it, which was to use symlink exchange attacks, the same attack we used before in 2018, apply it now to procfs. And this one's a bit more complicated to set up, but basically you can have two containers running, and you set one to have the volume from the other one, so you have a shared volume, and then this container is swapping the procfs files. So they swap two directories over, which are procfs, and then in this container, the procfs, there is like a chance that during setup, procfs will not be set up the way it was meant to be set up. Anyway, it was quite a clever attack, and you could do it with like 2 or 3 lines of bash. Effectively, this now you would think that what I just mentioned about, we have this protection against writing to procfs files, so it doesn't matter because we'll be able to write to it'll just fail to write to a procfs file. Unfortunately, it turns out there are 2 procfs files that completely make this protection useless. And I wrote this code to protect against this, so I feel a bit silly for doing it and not thinking about it. But basically, procself_shed is a file in procfs which you can write to, and it will do nothing. And similarly, procself_environ is the environment. Like when you set your environment, there's a file that represents it in the file system. Procself_environ, similarly, is a file that you can fill with any contents you like, and if something tries to read from it, it'll read it, and it's a procfs file. And as a result, we're screwed, because if you try to check if something is procfs, well, it could just be a bind mount to procself_shed. Very, very bad. We we've managed to solve this problem as well, but it's sort of a stop the bleeding patch, because this is a very fundamental issue with using procfs, is that because these proc mounts can be screwed around with by the container runtime when joining, it can't trust that proc is really proc, and as a result, you can end up with all sorts of attacks. And the solution, quote unquote, would be to have a handle to the host's procfs when you join the container. But again, now we're back to the game of let's have an open file handle to the host file system while we join the container. And I don't know about you, but to me, that sounds quite scary. So effectively, we have some protections against this, but it's a bit dodgy. And yeah, procfs is like staring into a bottomless abyss filled with pain and CVEs. It's pretty bad. Like the longer you see all these ways of attacking through procfs, and I did help come up with some of these. It is quite fun discovering how many things procfs can do, but also absolutely terrifying, like to the center of your soul. And yeah, volumes were a mistake, at least in my opinion, because a lot of these attacks are taking advantage of the fact that volumes are effectively, they allow a remote image that you download from the internet to configure your container. Now, the configuration it's not like it can configure anything in your container, but the fact that it can configure mount points is a bit scary, because mount points are sort of like the seedy underbelly of Linux, because there's a lot of dodgy stuff that happens with mount points, and it's kind of scary that you have all this configurability that like images you download from the internet have. It's kind of freaky. And yeah, now we come to this year, and I discovered some things which were almost CVEs. Now, these were security bugs that were in Run C, but they weren't in any released version of Run C, so there's no CVEs associated with them. But it was kind of interesting to find them. And this is, again, down to configuration. It turns out that the devices C group code we had, so the devices C group is sort of the only security-related C group, in that the devices C group allows you to limit what device access you can have is in a container. And by default, devices C group is allow all. It doesn't do anything. So effectively, there were several problems we had. One of them was that during Run C updates, during an update of any setting, not just a C group setting, not just a devices C group setting, but any setting, if you were to change the memory limits, it would clear the device access list. So it would allow anything temporarily. There was like a race window whether this would be allowed. This is because systemd clears this by default, and we didn't realize it at the time. So effectively, systemd C group systemd would clear it, and then we would set it afterwards, meaning there was this window during which the container was running, where the container runtime, where the container process would be able to access device files it shouldn't be able to access. And this can be quite bad, because images can arbitrarily inject any device inodes they like. So they could just run an image that has access to every device inode on the system, and then just wait for an update to happen and then write to them. So it's pretty bad. Luckily, this was never in a released version of Run C. We've already fixed it, but it was a bit scary because no one had noticed this at all. And the other thing was that our default devices policy was allow all, which is very, very bad. Like it was a deny list rather than an allow list. This was pretty bad. It turns out that, and this was a bug that I thought we had fixed in like 2013. Like if you go back and look at it, this was an issue that people brought up in 2013 that needed to be fixed. It turns out, and this is now where we get into like weird legacy code, Docker fixed this, but then when Run C was split out from Docker into a separate project, the code never got moved. So all users of Run C were protected against, because all users of Run C would explicitly set a deny by default policy before doing anything else. But Run C, if you were to run it by itself, it wouldn't do this. Again, this was fixed. I wrote the patches for this. There were a bunch of other weird things like related to intermittency, but they're not security issues. It was just sort of us being dumb. And yeah, it's just sort of, how is it possible for code this young to have a legacy code? It's ridiculous. Okay, so that's a very, I hope, at least somewhat short whirlwind tour. I appreciate I talk pretty quickly, and there was a lot to get through. But the key thing, I guess, is what are sort of the common threads between all these CVEs? And I would say the most obvious one is, well, the one is don't be tricked into misconfiguring containers. This is something which we can fix by just not being dumb. It's sort of, I guess, let's not screw up as much is sort of the moral of the story. But the other thing, the second thing, which is quite key, I think, is that file system operations are actually very easy to screw up, especially file system operations related to procfs. But even just general file system operations are kind of freaky. So I guess, the next step is obviously let's just make all the file system operations safe. If we can do that, we'll be able to eliminate a whole class of vulnerabilities, which is what Pedram mentioned at the beginning. So how do we do this? Well, let's just make sure we all agree on what the problem is to understand the basic idea of the problem. Is you have this path, you have foo-bar-baz, and you want to operate on this path. It doesn't really matter what you want to do. You want to create a file, you want to delete a file, you want to open a file for reading, you want to open a file for writing, you want to stat it, whatever. You want to bind mount to it, whatever. Well, okay, so foo-bar-baz, what do we do? Well, baz might be a symlink. Okay, well, that's fine, because nofollow, which is an open flag, which allows you to block following of symlinks, but only the trailing symlink, nofollow blocks this for you. Okay, great, we're done then. Well, no, what if bar is a symlink? Well, if bar is a symlink, well, we can try to sanitize it in user space. Like we can sort of do what Docker did, which is like, okay, well, we'll walk down, we'll go foo, is foo a symlink? No. Is bar a symlink? Yes. Okay, read bar, and then yada, yada. Okay, and that sounds all well and good, but what if foo is, I say attacker control, what I mean here is like if an attacker can modify files under foo, like they can do the rename exchange attack, well, then you're screwed, right? Because, well, if foo is attacker control, then bar can become a symlink after you sanitize it, and, woot got root, right? So how do we solve this problem? Well, it turns out that this problem is actually solvable in user space. As I mentioned earlier when discussing LXD, it is solvable, but almost no one does it correctly. This is sort of how you would do it, effectively. You have foo-bar-baz, and then you would walk each component. You'd say, okay, for each component, we open the next component relative to the current one. So we would open a file descriptor /, and then we would say open foo with nofollow. And if we open it, then that's the current file descriptor. So you do it step by step, basically emulating the entire path lookup procedure. And then once you do that, then you handle symlinks in user space by tracking the text path. This is a bit more complicated, but basically you have to handle symlinks yourself now, which is very fun. And then once you've done that, then you have to do some double checking along the way through procfs. Procfs allows you to double check that an open file is what you think it is. And so you can do this double checking through procfs. And then once you've done all of that, then you have a file descriptor at the end of the day. And then you have to only use that file descriptor, because if you ever touch the path again, the paths are unsafe. So you have to be dealing with file descriptor only. And very few programs are written this way because it's very hard to get right. And also it's sort of a pain in the ass because everyone assumes that paths are how you access files. So we're screwed, right? Okay, well, there is actually a solution to this. So this was the solution to making this easier is openat2. So openat2 is a system call that I implemented last year, and it has been merged. So this is in Linux 5.6 and later. It's a system call which allows you to open files, and in particular, the key thing here is that it allows you to specify the way that path resolution works. This is something which you couldn't do before because, as I mentioned, nofollow basically just blocks the trailing symlink. It doesn't care about the rest of the path lookup. So you have this structure. The way this system call works isn't super interesting. At least in this discussion, it's not super interesting. So basically, you have the structure and you have these flags. And of the resolve flags, there are a series of them that exist. You can block all symlink lookup. So if there is a symlink at any point during the path, you get an error rather than going through it. You can resolve magic links, which magic links are these procfs like proc self xc and proc self fd, the ones I mentioned. They're magic links, which are these file descriptors that allow you to sort of jump through into the host file system if you're unlucky. And then resolve no xdev blocks mount points. And resolve in root is basically like open this path as if I was in a ch root. But it's more secure than ch root because ch root has some trivial ways you can get around it. But in general, it allows you to do these lookups safely within a root. Okay, so we're all done, right? I mean, we have this openat2 thing. It might be a bit annoying to use, but hey, we can just use it, right? Well, not so fast. Unfortunately, it's even with openat2, it's hard to get this stuff right because first of all, if you run a program on an old kernel, remember openat2 is only Linux 5.6. openat2, you still need to harden programs on old kernels, and On old kernels, you'd have to fall back to the old way of doing things, which again is very error prone. And even with opening files, you need to, I mean, most programs do more than just open a file, right? They do a variety of things other than that. They have to try to mount to things. They have to create symlinks. They have to read and write to files and all the rest of it. So it requires more work than that. Just any program doesn't work in that. So you would have to be very careful when using these file descriptors to make sure you don't misuse them in such a way that you accidentally start resolving paths inside the container, because again, that will cause security issues. And then, yeah, programs need to be restructured to use file descriptors everywhere. Because, again, paths are scary, paths are dangerous. You can't just take the file descriptor and then use it. You can't take the file descriptor and then like convert it to a path and then use the path. You have to rewrite your programs so that they use file descriptors everywhere for basically everything, which is complicated and requires a lot of work. So what we need is, I would say, a library to make path resolution safe. And if you sort of squint a little bit, you'll see, libpath. Okay, so libpathrs is a library that I wrote to make path resolution safe, and rs it's also written in Rust. So libpathrs is trying to solve this problem by making it so that we have one library that does all this annoying crap for you. So it's a Rust library with C bindings, so you can use it from basically any language. It currently has bindings for both Python and Go, and there'll be more bindings, I'm sure, for other languages eventually. As well, obviously, you can use it in C and Rust. It emulates OpenAT2's resolve in root on older kernels, so it does this path lookup thing I mentioned. And it implements some helpers that match most VFS syscalls. So it eliminates this problem of open isn't enough, because it has the wrappers for making directories, removing directories, unlinking files, linking files, and all the rest of it. And it also has some additional hardening related to procfs, which is something we'll get into in a little bit. So what does it look like? From Rust, this is how you would use it. So you would open a root to, we can say this is like the container root file system. You would open a root, and then once you open the root, you would then resolve path relative to the root. You would get a handle, and then this handle can then be reopened with a particular set of modes, which is that's basically opening etc password inside a container read-only. The reason why there's this separate resolve and reopen stage is because basically within containers, there are some files which, if you're clever, you can half open. So this resolve is like half opening it. So it gives you a handle to the file. So if the file moves, the handle still resolves to the same file. But it's not fully open in the sense that when you reopen it, it actually does a full open from scratch. And this is important because certain files, like for instance, pseudo-terminal controllers, which is something that we use in containers during setup, they are ideally something which you want to be able to reopen multiple times so that you can create a new console for each new session without having to touch the container file system. That's sort of the short version. But basically, for most users, that's what you do. In C, it looks like this. It's a bit more ugly because C doesn't have nice error handling APIs, so you have to sort of do the whole if error crap. But it looks basically the same idea. And you can now do this within C, and Go. The Go example is similarly simple, and the Python example is even more simple. If I have time later, I'll show you some examples of the code that what it looks like. And actually, I was going to do that now. Okay, so let's go give a quick demo. So I should probably mention, while I was talking a lot about containers in this talk, this path resolution problem is actually a more generic problem than just containers. Basically, any program that has to deal with a directory which attackers have access to, like have the ability to create files in, is potentially risky, I would say. So this might include things like FTP servers or web servers. This might include, source control servers. Like you can think of all sorts of examples where if you have the ability to upload files, or if you have the ability to trick the system into creating a symlink, you can start getting into pretty dangerous territory. So I'm going to give a sort of a quick demo is sort of too strong a word. I'm going to sort of just show you a couple of examples. So this is actually, let me go to an example program first. So this is an example Python program that uses libpathrs, as you can probably see there. Hopefully that's big enough. I'll make it a bit bigger so it's easy to see. So it uses pathrs, and what you can do is that you can open a root, So what this does is that this is basically cat, but safe, hence safe cat. It will open the root, a root handle to whatever path you have, and then it will copy the content. Sorry, that's old code. And then what it'll do is that it will resolve the root. It'll resolve some path underneath it, and then it will open it for reading, and then it will read it, and then it'll print the output. So if I do, so inside this rootfs, we have this totally safe directory, which if we look at, it actually tries to get to Etsy password. Okay. Now, normally, if you were to cat this thing, you would get my host Etsy password. But if I use tests safe cat, rootfs, tests rootfs, and then you don't. It's still inside the container because they're inside the container. There is Etsy password that is inside the container. So this is like a silly example of like you get all these nice benefits, but it's a fairly easy library to use. As another example, this is like a static web server that basically does something similar. So it first, when it sets up, it opens a single root handle for the entire web server, and then it resolves whatever path you try to get at through Flask. It'll open the file and then it'll serve it, but it's defended against // attacks and these other tricks, and symlink attacks and all the rest of it. And as a bit of evidence that this actually does protect it against the particular attack I mentioned, this is like a Python file that's like a test file, which does the attack here. So what it does is that it swaps A/C and B using rename exchange. And then the victim here tries to open C/Etsy password. And if it isn't open inside the container, it starts screaming. So if I use it, it works fine. And if I do, it should mention that because this library supports both the emulated and the kernel modes, I can tell it to use the emulated mode. So this is like as if I was on an old kernel. If I run this, it has the same. It doesn't ever break out of the container. You do get errors, obviously, because if it hits the race condition, you might get an error, but it won't ever access the host. And if you don't believe me, if I run it with insecure, this is going to run it using code very similar to how Docker does lookups, and you'll notice that it broke out of the container a lot, right? Like it's pretty bad. So that's sort of like a very quick example of what it does and what you can use it for. And I'm hoping that a lot of programs will be interested in using this thing. So yeah. So now we're all done, right? Well, no. Let's have a quick chat about procfs. Procfs being sort of the bane of my existence at this point. So procfs there is another problem, which is that procfs is very important to container runtimes because it is something which we use very critically. Like, it's very critical to the security of containers because we use it a lot for protecting containers. So the question is how do I make sure that I'm writing to the real procfs file? Because if I want to, this sort of harkens back to some of the attacks I mentioned earlier, where the attack is we just trick runc into not writing to the real procfs file. So how do we protect against that? Well, what you can do is you can try to grab a proc handle. So you open /proc. Now, luckily, there is actually a guaranteed way of checking that /proc is a real procfs and isn't a bind mount, which is that the inode number of /proc is 1, and there's no way of faking that. It is /proc always has an inode number of 1. Okay, so we can get proc, but how do we get all the way down to exec? Well, you can check if the target is a procfs file, which I mentioned we already do, but you aren't sure it's the right one. So what you can do instead is you can just disable all symlink crossings. So you can either use openat2 or you can emulate it to just block symlinks. And okay, well, if the only thing we have to worry about is symlinks, which, a bit of a spoiler, it's not, but if we say it is, then if we can't cross symlinks, then we can be guaranteed the final file we open is actually what we expected. But then if you think about this for a second, as I did a few months ago, how do you deal with bind mounts? Because, okay, symlinks are one thing, and we can block them, but how do you check bind mounts of, whatever? What if proc self attr is a bind mount to somewhere else? How do you deal with that? Or if proc self attr exec is a bind mount to something else? Well, yeah. What about bind mounts? Like, how the hell do we deal with this thing? It turns out. So I know that this is a one-way conversation, but I'm gonna ask the hypothetical question anyway. Put your hands up if you think it's possible to be able to detect bind mounts on Linux today. Is it possible for you to detect whether or not something is a bind mount? And I'm going to assume most people thought, well, I don't know what you thought. I can't hear you. But I would say, at least to me, I expected that it would be possible because it's something which seems pretty obvious. Well, it turns out, no. It's actually not possible. There is no way on Linux to be sure, and that's a typo, but never mind. There's no way on Linux to verify if you've crossed a bind mount, if you're touching a bind mount, until OpenAT2. OpenAT2 is the first instance you can do it. So that means on old kernels, there's no way of protecting against this because you can't be sure if something is a bind mount. Because all of the ways that you can think of checking whether or not something is a bind mount are flawed. So if you were to look at the mount table can both change underneath you and it can be a fake mount table. If you try to check the file system type, well, it can be the same file system. It doesn't have to be a different file system. And you can try to check generation numbers, but that is pretty dodgy. Basically, there's no way to do it without OpenAT2. So we're screwed on old kernels. Well, okay. Well, what I thought at this point was, okay, well, we can't protect against it on old kernels, but we can just say, okay, well, maybe bind mounts make this slightly less secure, but whatever. It's not a massive problem. Because, well, we can just do the checks for if it's on the same procfs, and it shouldn't be too bad. But then you start thinking about magic links, which are these magical symlinks that let you jump to anywhere in the file system. And then there's magic links, right? Then you hit the magic link problem. So what's the problem with magic links? Well, so you have like proc_self_fdn. You have these two types of magic. You have two examples of magic links. So the thing is that these magic links are so OpenAT2, when you block mount point crossings, it also blocks mount point crossings through magic links, because obviously if you ask me not to cross mounts and a magic link will cross a mount, I'm not going to let you do it. Well, what that means is that proc_self_fdn, whatever, these magic links, you can't ever be sure about opening them because you have to allow bind mounts, but someone could have bind mounted partially over it, right? Like so in other words, you can't be actually sure that like you have to allow crossing mount points, but what if it's not crossing mount point you expect? But then I thought, and I don't know, maybe you aren't following me on this one, but at least for me, I thought, well, okay, well, magic links aren't that bad because what we could do is, okay, there's proc_self_fd. Now, if we go through proc and then PID and then FD, there are no symlinks in that path. So we can block all symlinks and all mount point crossings. And then once we have a handle to proc_self_fd, we can say, aha, now I will allow magic links. And because it's not possible to bind mount over a symlink, because mount does follow symlinks, because it's not possible to bind mount over a symlink, it'll be fine because this handle will allow me to open things. I mean, we can all sing Kumbaya and it'll be great. And the same thing for proc_self_fd. And that's what I thought. And I was so convinced of myself until the second that I tried to bind mount over symlinks. And it turns out that yes, you absolutely can 100% bind mount over symlinks. And it's very, very funny when you do. Basically, there is a way to do this thing where you can, if you open a file and then mount over the file, you can basically trick the mount system into allowing you to mount over symlinks, which means that there is absolutely no way of being sure this stuff is safe, because now when you try to go to a magic link, this magic link could jump you to anywhere. And again, we use proc_self_fdn inside container runtimes for security reasons, as well as proc_self_exe. These are both very, very important facilities in container runtimes. And yet, we can't ever be sure that they're safe, because if something managed to bind mount on top of them, then you're screwed. And it even turns out that actually there were kernel bugs involved in this, because if you tried to unmount them, it would actually cause kernel crashes because there was a bug in how this whole thing worked. And also, if you have this bind mount on top of a symlink, if you try to unmount it, just do like, let's imagine I bind mount over proc_self_exe. If you try to unmount proc_self_exe, it doesn't unmount the mount on top of the symlink. It unmounts the thing the symlink is pointing to, which was very hilarious when I accidentally unmounted like my host file system on my laptop when I was testing this. But yeah, basically we're screwed, and I don't know how to solve this problem. And it's a very, very deep problem because it's sort of very fundamental to the security of containers. Okay. All right, that's the incomprehensible rambling section over. Let's move on. So I don't have a solution for that, but for the next steps, at least we can try to solve sort of the core problem. So my next steps are I'm going to stabilize the base C API for libpathrs so that it's more stable for everyone to use. And then I'm going to start porting programs to libpathrs. The first programs we'll probably start porting is Umochi, which is a tool I wrote for container images. And then eventually we'll port runc once we have a good handle of how painful porting will be. And yeah, there's more kernel hardening work to be done, which I've gone a bit over time, so I might not have a chance to talk about it. But if you want to ask questions about it, I can get into it. And yeah, once we add this hardening work, libpathrs can add support for it opportunistically. So getting people to switch to libpathrs means we get some security, some pretty significant security benefits, and then we can slowly add more later. And there's a lot of work needed to make procfs safe to use. I mean, it's absolutely ridiculous. Yeah, so links you can find OpenAT2. It's now in Linux, and there are a couple of LWN articles. I'll give Pedram the links to the slides later, so you don't have to write these down now. But there were some LWN articles about it, and now if you have an up-to-date system, it's in the man pages. libpathrs is on GitHub. It's a Rust library, so the docs are also on docs.rs. And you can get my talks from github.com/cypher/talks. And yeah, that's all I've got. Any questions?
Beautiful. That was quite a nice talk. I can feel the energy, hey? And it was quite a short time for you to give us all those backgrounds and talking about the how Linux kernels handle this, and also on top of that how the runtime works, the containers runtimes work. So great job on that. We do have quite a few questions from our viewers, but I have plenty, so I will let those Minto ask first. Craig, do you want to help out with that? Yeah.
So when security level, it's both SE Linux and AppArmor. So SE Linux obviously is well known for having security labels as like a core feature, but AppArmor profiles are also represented as labels. As like if you have an AppArmor system and you go to proc self attr exec, it'll show you the current AppArmor profile you're in. When I say labels, that's what I'm referring to. I think Tamayo, I think that's what it's called. The other LSMs have something similar.
Another question from Mark Eldridge. Is the implication all software needs to be written to use libpath rs or equivalent in order for us to trust that they're properly limited to the container FS? And what does this mean for multi-tenancy?
So it depends what software it is. For container runtimes, we need to do it because our job is to set up this container file system and operate on it, and sort of we're part of the security barrier between the container and the host. Programs that run inside containers are pretty much safe because you're sort of depending on the kernel to do this defense. The issue here is that programs which are privileged on the host can be tricked into doing things that they didn't intend. Basically, it's a confused deputy problem. It's like a textbook example of it. As for multi-tenancy, I would say, again, it depends. Like if you're running like a web service, for instance, this is the trivial example, or an FTP server is an even better example. For FTP servers, if you have like FTP servers that have potentially malicious users, then you would care about this type of protection. But like if you're only running programs inside containers, then they don't need libpathrs.
Another one from Irvin on YouTube. How can you fake /proc/mount? That should tell if it's the bind mount. And the second part of that question, or proc self mount.
You can bind mount on top of them. So if you bind mount on top of proc self mount info, or if you proc self mounts or whatever, there are a couple of ways of doing it. But you can just bind mount over them, and then you can't tell that it's real, right? And as I mentioned, proc self environ is an example of a file that you can fill it with any contents you like. So you can set the environment to look like a real mount table, and then you bind mount that on top of proc self mounts, and there's no way of telling that is not mounts because it is a procfs file and it has mount-like contents, but you can't be sure that it's real. Oh, and the other problem is that even if you were to check it, there is a race condition where after you've checked it, then something could bind mount afterwards, and then when you do the operation, the mount table's changed. So even if it was safe, it still would be bad because the interface is such that there's like a time of check, time of use.
Got a question from Rekim64 on YouTube. Should we go back to VMs instead of containers for security? And more seriously, if programs aren't run as privileged in the container, will this reduce the risk of security issues?
Yes, it would. And actually, what I mentioned earlier about user namespaces, that is basically running them with less privileges, where you basically don't run them as root, which is something that I've recommended for years and people have recommended for years. But even better is don't run them as root and also run them inside a user namespace, because user namespaces, I didn't have time to get into this, but the container, basically, a lot of the hardening mechanisms in Linux. So I mentioned this dumpable flag. There are some hardening mechanisms in Linux that only are effective if you use user namespaces. So if you use user namespaces and you don't run as root, many of the issues I just mentioned are not real issues for you. Container runtime still have to fix some of these issues anyway, because, I mean, an unprivileged user can create symlinks. But some of these more complicated bind-man attacks aren't possible if you're not privileged inside the container. And no comment on the VMs point.
Perfect. I think that's all the questions we have online. Pedram, I think, had some as well.
Yeah, I do have. I think there's one on IRC. Can you give an example of Magic Link example that you mentioned?
Sure. Yeah, if you can just share my screen, I can give you an example. That's probably the easiest way of doing it. Right, so let's say, so I'm going to create a file, and I'm going to create, so tail, this just opens the file for reading. And then if I do pre-grab tail, so if I look at proc this PID, so so if you look inside this like procfs directory, so this is obviously procfs, that's the PID, and then inside, if you look inside this, it's full of like a whole bunch of crap, which, I mean, is interesting, but not important now. Inside FD, you have these things which look like symlinks. So if you look at them, they look like a symlink, right? If I do read link of, you know, if I do read link of that, it looks like a symlink, it tastes like a symlink. And however, you might know something odd over here, which is that this is like not what the normal file modes for symlink look like. The reason why is because while this thing is like a symlink inode, procfs is an in-kernel file system. It's a virtual file system, so it's not backed by a disk. It's just like memory the kernel like just maps out for you. And as a result, these symlinks, when you open them, it's not the same as going to a regular symlink. You may have learned when you did like Unix 101, when you open a symlink, it's like replacing the contents of the symlink into where you hit them. These symlinks aren't like that. These symlinks, when you try to open them, they will actually open the underlying file. So these actually link to the file handle in the system, and it like goes straight to the struct file like in kernel, and it does an open operation on them. So if I was inside a container and I had access to this magic link, I could open files on the host, even though the symlink wouldn't resolve to anything, basically. And it's like if I do, I mean, I can do, yeah, like if I open 3, like I'm reading and writing to the actual underlying file. Now, obviously, it's on the host, so this is a bit of a contrived example, but this magic link would also work inside a container if it had access to it. So hopefully that explains that better.
Yeah, yes, it does. So that effectively means that we need to have that mount point in container for that to happen.
Yeah, well, yes and no. So the issue is that when a process joins the container, it joins the PID namespace of the container, and the procfs mount inside the container has like that process in it now during the joining phase. Now, the dumpable bit blocks us from accessing it. So if you're using these namespaces and it doesn't have enough privileges, it's blocked from accessing it. But like the blocking is just like it doesn't have access to it. The magic link, if it could have access to it, then it could access the host file system. And this again boils down to the fact that there's one VFS for the entire system, which means that these file handles are not associated with the container. So if the container tries to open a file, tries to access through this file handle something on the host, the kernel doesn't know that it's not meant to access it. And there are actually some protection. There are some ways we can try to defend against this. I have some proposals, some upstream kernel proposals to block them, but it's still like a fairly fundamental issue of like, if you go too far in virtualizing these things, you start going down the VM path, basically. And the other thing is that these magic links are incredibly useful. Like, I didn't mention this, but in runc, we use them as like a core part of some of the security hardenings we have. So we can't disable these features, but because there might be bugs originally, but now they're features we depend on. And at the same time, they can cause issues.
Cool. I guess we got one more here.
Yeah. Okay. My goal is to have it done by the end of the year. No, sorry, that's a lie. My goal is to have libpathrs done and Umochi ported by the end of the year. So Umochi is a container runtime container image tool, which is used for building images by a variety of people. I would say that once we have that done, runc shouldn't be too bad, but I probably shouldn't speak too soon. There are a lot of things that runc does that are quite difficult. Like, for instance, you have to deal with the fact that runc requires mounts, requires being able to mount things, and also runc has this, because it's a Go program, and I used to like Go. And then I started working on container runtimes. Because Go has these very annoying limitations in regards to Cisco. I mean, I can speak about this for hours. Basically, Go, it might call itself a systems language, but I mean, I wouldn't call it that. And as a result, Go has these limitations with syscalls. So as a result, runc has to like create a whole chain of programs, and I imagine that libpathrs, as currently written, might not like it. So I imagine there'll be a lot of painful transition things. I would hope that early next year we would have runc ported. I'm hoping it'll be earlier. If there's no issues, I mean, porting it should be easy. But yeah, that's my answer.
Awesome. All right, so a couple of questions. One was in relation to that past sanitization, that you see the fix that they would put in place originally in Docker in response to your 2014 bug fix. How did they did the sanitization? Like, was effectively, hey, is this a symlink? So I don't follow anymore. Yeah. Was like that?
I actually wrote it, so I'm
okay.
partially to blame. Yeah. Basically, the way that it works is that it's sort of how I outlined in the slide where I talked about walking down the thing. So you have like /foo/bar/baz. What you do is that you check, you go path component by component, and you say, is this component a symlink? If yes, read the symlink and then like adjust the path, the previous part of the path, so that it's deals with the symlink, and then we go into the next component and the next component and the next component. Basically, it's like emulating the way that you would think of how symlinks are resolved, but you just do it in user space. The issue is, and this may sound similar to how I described the safe way of doing it, the issue here is that after you've done all these checks, at the end you end up with a string. And then this string is then passed around Docker in all sorts of places. It's stored in structures and all the rest of it. And then after some time, it then gets opened. The issue is that, okay, it may have been true that when you made this string that this was actually a safe path, but immediately after you're done, it's no longer safe, right? In Docker's case, it's never safe because they don't use file descriptors, and I guess, again, blaming me for this. We don't use file descriptors to do this lookup, so it's all done by strings, so it's never safe. But in principle, like, the idea is similar. It's just that you need to stop thinking about paths as the reference to files and instead file descriptors. Because file descriptors, if a file is moved, the file descriptor moves with it. So even if an attacker tries to mess with you, opening underneath a file descriptor to a directory is still that directory. Like, it's not switched to a symlink or anything.
And by that the string you mean? Yep, sorry, go
on. Sorry, another question from Mike. Would it be quicker to port runc to Rust?
Unfortunately, no. Actually, funnily enough, Oracle tried this. So there is actually it's now dead, but there was a project called Railcar, which was basically a rewrite of runc in Rust. sadly, the guy who wrote it, who I haven't met, but we worked online before. The guy who wrote it, we didn't chat about this beforehand because I'd known about all these issues at the time, and I really would have loved if we could have sat down and hashed out like a better designed Run-C, because there are many things in Run-C that are like very, okay, I'm not gonna say very poorly designed, but let's say questionably designed, and an opportunity to rewrite Run-C from scratch. I mean, it's the whole second system syndrome, right? Like we love to rewrite things, but we never get it done. If we manage to get a rewrite of Run-C done, there are many things I would want to fix that would improve both the security and usability of Run-C. So maybe one day we'll rewrite it in Rust. But I'm not sure it would be simpler because there's so much. I mean, I don't even get started about all the cruft that's in Run-C. And like there have been cases where we've made like very minute changes, and then like Google comes screaming that we broke like half of the containers. So it's very terrifying code to work on, which isn't good if you're trying to make it more secure. Yeah.
I guess Mark can potentially help out to port that to Rust. Just coming back to that example, the pass sanitization. So effectively, once you get that string effectively at the time sanitized and safe, you mean by that time the attacker can make a symlink to another unsafe place.
Yeah, like
the actual read can happen, like a talk2 classic example there.
Yeah, so if you imagine like you've taken foo_barbaz and the safe path is foo_bar_foo or something, foo can get changed the second that you return this string to the caller, and there's no way of the caller knowing that it's changed.
So in all these examples of most of those CVEs, the threat environment is that we got the attacker with a lower priv type account, and we got the container running with a higher priv, effectively root. And all these type of attack scenarios does make sense for someone to do. And we also need the attacker on the same host as the container engine, right? Is that the case?
Yeah.
Or
but
access to that host.
Yeah, but I mean, if you have access to run, I mean, like if you think of like GKE or something, you have access to run containers on GKE. You can attack the container runtime on that node that when it's trying to do operations on your container. And like Kubernetes, for instance, for some reason, I don't know why, Kubernetes, like it pounds C groups a lot. And so if you ever find like a fun issue with C groups for Kubernetes in Run-C, you're going to hit a case where any container running in any pod on any Kubernetes cluster would be able to break out. Now, I don't know of any bugs like that, but I mean, it's entirely plausible, right?
Okay, so do you mean like within the container, you can effectively do some of these attacks? You don't necessarily need to have a host access.
Yeah, so all the attacks, I probably should have explained this better. So all the attacks I'm talking about where we're trying to access files, these are being accessed from inside the container. So this is the process that is being configured to be inside the container, or it's a container runtime on the host trying to operate on the container, and it ends up trying to touch files or touch procfs or whatever inside the container. And so therefore the container code inside the container can try to mess with it. So you don't need host access for I don't think for any of them you don't need host access. The most you need is privileges to start containers, which is enough privileges on, like, I mean, if you think of like most public clouds, right?
So effectively, all those symlink race conditions we were talking about, you can actually do them in the container and get arbitrary access to those files. All right,
yeah.
That was a good clarity there. One thing that I found quite a lot of people have issues with capabilities. Is it your area? Defining cap drops, cap all. Is it an easy way for people to define those for effectively limiting those syscalls?
Yeah. So I mean, so capabilities are something which people should be configuring normally. Sorry, in general, I should say, people shouldn't be running code as root, right? Like most programs don't need to run as root. And in containers, root has a limited set of capabilities by default, at least under Docker and LXC and LXD and all the rest of it. Ideally, you would set the privileges to be as minimal as you need, like the smallest amount you need, least privilege, all the rest of it. Capabilities are like relatively easy to configure. They're not terrible to configure. There are annoying things, like for instance, if you want ping to work inside your container, you need to enable capnet raw, which is like way more privileges than are necessary. And there has been work to try to fix some of these issues. Like for instance, ping on modern kernels and modern containers, ping will just work because there was work done to make this not require setting privileges. The other thing is that capabilities is one step. Another thing that people should configure is SecComp. SecComp is a facility for basically filtering syscalls. This one is way harder to set up because, again, think of like all of the syscalls your program may run. It's a fairly big set. Docker and LXD by default, they have a set of syscalls where they only have like an allow list of X hundred syscalls rather than all of them. And this has protected against CVEs in the past. But ideally, people running these systems should have SecComp profiles for their containers. This is like in an ideal world. Though practically speaking, it's kind of difficult to get this stuff right because we're talking about like if your program hits a syscall that it didn't hit when you were testing or developing this, your program crashes. It's not good, right? So it's a bit more work.
Don't you fall to the same situation with the capabilities as well? Like if the program may not show or require all those caps right at the start, but after you put it for a while running and there was a call and suddenly and often how do you find what are those? Like this is just you need to enable one by one and then figuring out, oh, okay, I also need to add this.
Yeah, it's a bit annoying. In theory, audit logging can help. So for instance, AppArmor, to switch a bit, AppArmor lets you have this like complain mode where you run it and it will just spew warnings at you. The program will still run, but it'll spew warnings at you telling you, you tried this, but you didn't have the right privileges. We've let you do it, but this is what you were missing. And this can help you create a profile, an AppArmor profile. SecComp now has something similar. It has a log action, which is sort of similar. And then for capabilities, there's not really anything like that. I mean, in theory, I think that audit logging you could use, but I don't know much about audit. Like as in like in kernel audit, there's an audit framework, and I've never really used it much. All I know is that it's kind of complicated. But the thing I would say is that for capabilities, luckily there's only a couple. There's like 30 of them, so it's not the case that you're going to spend like 3 weeks trying to get this working. And in most cases, right, like, does your container need to load kernel modules? If the answer is no, then you can like disable like 5 capabilities. The one important thing is to make sure that you don't run with capsysadmin, which is the big one. That's the one that that's basically like when you enable that, you're enabling root, like real root, pretty bad. And similarly, there's also for run C, because a lot of the protections we have depend on this non-dumpable flag. Also disable capsys ptrace. I mean, use user namespaces, but capsys ptrace actually like disables a bunch of these security features, which you wouldn't expect given that it's called capsys ptrace. You'd think like, oh, it's like for debugging. No, it turns out that a bunch of these like debugging flags are actually security features, which is, I mean, we can have a discussion about the security design of Linux another time, but it's not good. Like in terms of like it's like a Rube Goldberg machine. Like the amount of weird shit you have to enable and like all these. It's just ridiculous. Like the fact that it's not as simple as doing one thing to set up a container is insane. But also the fact that there are like all these various, I've only mentioned a couple of them here. There are many, many more like weird things that we do during configuration to make containers more secure. And I'm actually not sure how I would have discovered them if I wasn't involved in kernel development or if I didn't know people who had hit these issues before me. Like it's nuts that that like security on Linux is basically a Rube Goldberg machine to get it working. It's absolutely crazy.
Wow. So just like expanding on the exact same point, weren't like, because some of these past resolution issues that you were talking about, it seems to be like, is the first time the container world is hitting those. But weren't those sort of issues previously been at least addressed or some lesson learned from, I don't know, FTP or Git or some of all these that you could borrow potentially?
You'd think so. You would think they'd been solved, but they haven't really been solved. I mean, there are the solution that a lot of people went with for a long time is to just run in a CH root. This is actually what Docker does for Dhaka CP. That is a solution, and it does work. The problem is that it's inefficient because if you imagine, because in order to run a CH root, you have to spawn a new program. So imagine if every single time any system had to open a file or symlink a file or anything like that, you have to spawn a new CH root, a new program, exec a new program, and then get that program to CH root inside the system, and then do the one operation, and then return it back to the host. It's ridiculously wasteful. And the emulated thing I mentioned before, the emulated mode, is also wasteful, but it's 50 syscalls, but you don't have to exec a program, because on Linux, fork exec is expensive, like pretty expensive. And And then OpenAT 2 is even cheaper, like in that it's just one syscall, and it takes advantage of a bunch of in-kernel features that allow you to do this protection. So people have thought about this before, but I think that people were just sort of happy with CH roots, and I think that it wasn't understood. I guess like in the more olden days of Linux and Unix, multi-tenancy was not. It's not that multi-tenancy wasn't common. It's that running other users' code inside a like protection thing wasn't common. And a lot of the operating systems that are sort of forefront on these types of security developments, like, I mean, in the olden days, it would have been, Solaris and FreeBSD, which have jails and zones, or zones and jails, respectively. They don't have these issues because they have in-kernel concept of a container, which lets them fix many of these issues, meaning that for them, they weren't even problems. And FreeBSD, funnily enough, has something similar to OpenAT 2, though it isn't quite the same. But I did look at it when I was developing the Linux one. But the point is that little bits of this have been dealt with, but I think there hasn't been someone saying like, no, we need to actually like sit down and fix this. And yes, you're quite right that this is not just a container problem. It's a problem that like FTP servers would care about. It's a problem that web servers in theory might care about, Git, all the rest of it. Yeah.
That makes it more scary then.
Oh yeah.
Not more scary. Now, one of the things I always ask is around whoever wants to get into effectively learn more about container security, run C, and you talk a lot about /proc, and that's a big word there. What would you suggest as like a starting point, references, things that helped you out previously, and would be a good resource for them to take and start effectively pushing some issues for run C?
That's a good question. The problem is, I guess, that a lot of these sort of like dark internals of Linux aren't very well documented. Like magic links. I mean, I actually wrote when I was writing my patch for OpenAT 2, I wrote documentation on magic links. It turns out that this is like something which it didn't even have a name. There wasn't a name for it. I mean, I made it the name magic links up, right? Like they were referred to as like, actually, sorry. There was no name. There was no name at all. And in the documentation, there is no documentation on some of this in the kernel tree, but it's like, it's not enough. As far as getting started, I mean, to be honest, for me, just playing with it is how I found most of the stuff that I found, which is a bit worrying in that no one else played with it to find this stuff out, but okay. But I would say that that's one thing. I would suggest for people who want to get involved in some of the more security side of things of like of kernel development, it's sort of the general rules of kernel development in general, which is you go on LKML, you go and read. For the Procfs stuff, it's mostly on the file system dev mailing list. I would suggest go reading through some emails. For me, at least, it took me quite a while to get accustomed to kernel development. I mean, it's a fairly complicated program. I mean, it's, especially the file system portion of it. I mean, the file system portion of the kernel has gone through like 25 years of like optimization. Like you read it and it makes no sense at all for like the first like 3 months of trying to understand it. Luckily, there is some more documentation about things like that now than there was when I first started. So now you can go and read the kernel docs, which are getting a lot better. So that's on the kernel side of things. On the run C side of things, I don't know. I mean, I would say this is something which we are lacking. We are lacking sort of getting started for these things. Mostly, to be honest, I think it's because now it's sort of chicken and egg. There isn't a lot of interest, and I wonder whether or not the reason why there isn't a lot of interest in sort of boring kernel work is actually because there isn't enough help for people. Yeah, I would say, look, you can email me, and I can see if I can give you some pointers. I'd have to think about it a bit more because it's there isn't any obvious place to go to, unfortunately.
All right. Okay, I think at least I know quite a few students might be very interested in this topic, but as you said, there is no clear starting point where they can start to learn step by step, unless similar to yourself, deep dive and figure it out as you go.
Yeah, I try not to drown.
I guess I want to limit my questions there, but thank you very much, Alexa. It was awesome talk. It was really interesting. The talk will be there in our YouTube channel. So typically we get quite a lot of hits right after the talk. So there will be some comments, some questions. If there's something came around, we will pass it on.
Sure.
But with that, I guess, thank you very much. And I hope we see everyone at the next SecTalks in August.
Yeah, and I can't wait for us to be able to meet up in person again. It'd be great.
Likewise, pretty much.
All right.